I think we are good to start the second talk of today with Erik Panzer from the University of Oxford, telling us about tropical quantum field theory and asymptotic of perturbation.
Thank you very much. Just when should I finish? Because of the time on this one.
Sorry, 1 hour.
1 hour. Thanks for staying or coming back. It's a great pleasure to talk with such a big audience around here about the recent work I've been doing for a couple of years, but it took a postdoc to help me. So this is in collaboration with Paul Hermann-Baldorf, who is with me in Oxford at the moment. And the title is a bit weird, and I understand the topic is a bit weird, so I'll try to be very, step by step. I mean, we're all weird, right? So please ask me questions at any time if something is strange or cool or whatever. This is not the standard way how people think about things, and I'm aware of that. So I'll try to explain and motivate why I think this is interesting. But my goal is to convince you that there's some interesting mathematics here. So I'm working in the setup of very classical perturbation theory, just like in the talk before. So the idea is you want to compute some quantity, be it an amplitude, some collision of particles, or you can also apply this in condensed matter or for gravitation, as we've just seen. Somebody told you if you open a textbook, you have to sum a lot of diagrams, and for each diagram, there's an integral to compute. And these integrals are called Feynman integrals. This is actually unfortunate. That doesn't really matter what's on the bottom. It's just, you've already seen some of these integrals in the previous talk. You can write them in many different ways. The point is, for every graph, you have to compute some integral. And there's huge machinery how to compute these integrals. You have to integrate over loop momenta and whatnot. But what I really don't want to talk about doing these integrals. I've been doing this for many years, and this talk is about something else. The main message is that the idea is if you compute more and more of these diagrams, you compute more and more of these integrals, you get a higher accuracy prediction for your quantity. Right? So you can go to higher orders in whatever perturbative expansion you do. Here I've written the expansion, the coupling constant, which is like the standard case, but you can also expand in other limits like we've seen just now. But there's, of course, many problems with this approach. Let me just highlight some of them. So one is just the pure computational complexity. These graphs you've seen already for this calculation you've just seen, there was already 9 indices on these integral families, and you had some non-trivial differential equations. And if you go to the cutting edge of what's happening for calculations at collider experiments, you get not just logarithms like we've seen, you get polylogarithms, Calabi-Yau manifolds, all kinds of crazy functions, beautiful algebraic geometry, Calabi-Yau manifolds. But of course, it's beautiful, but also hard if you want to do all these integrals. And I will not say anything about that. I'll focus on another problem in the setup, which is that suppose after a lot of work with AI, who knows, you get a black box who can compute all of these integrals for you. Suppose all Feynman integrals have been computed for you. Then you still don't know what to do. Because if you actually try to sum them up, you get infinity. So this is very well known. This goes back a long time. That the way that these classical perturbation theories are set up is that you're kind of expanding around an essential singularity. So actually the perturbative expansion you get is a divergent series, and the coefficients. So if you sum more diagrams with n vertices that correspond to the alpha to the n term in this expansion, it's not like a Taylor series that you just sum up. The coefficients grow like n factorials. If you remember your calculus, the radius of convergence of this power series expansion is 0. So if you try to add them up, you just get infinity. This is, of course, a conceptual problem. So the idea, how can you even make sense of perturbation theory if you already know going in that the sum is infinite? What's the whole point? And how can we get any reasonable numbers out of this? Right? So you can only scratch the surface here. Sorry?
Subclasses that don't suffer from this problem. Right? If you look at planar.
There are, I will say about this.
Limit in n equals 4.
I will get to this in a second, yes. But this is like the generic situation. If you go to theories like phi to the 4, scalar theory, quantum electrodynamics, quantum chromodynamics. I mean, phi to the 4 is established, and phi to the 4 we know that the series is factorial divergent. As soon as you go to gauge theories, there's already the level of rigor. It goes down, and there's some questions. There's even some hypotheses, maybe in QED, some gauge equivalent classes actually are convergent, who knows. So even just establishing the growth rate of the series is difficult, but in my talk, I will focus on this phi to the 4 case scalar interaction where we actually know at least something. But my main message is that from my point of view to this day, we know very little about what's really going on in large orders in these perturbation theory. And I want to approach this from the point of view, well, suppose we know all these, what's the point in computing perturbation theory if we know that these things sum to infinity, right? So that's what I want to focus on today. And of course, there's machinery, there's Borel resummation, there's research, there's a huge mathematical toolbox on how to get data, reasonable predictions out of these kind of series. But the starting point is that you should know what this behavior of the series, how does it actually look like before you can start applying these methods. So how can we try to have a window into this? So there's try to review several kinds of simplifications you can try. And one of them is some kind of, you go to an integral model, you go to 2 dimensions, you introduce some supersymmetry, you go to a planar limit, a large n limit, those kind of things. So there are beautiful calculations using very sophisticated methods and integrability and other techniques where in some cases you can exactly sum the series. But this, in most of these models, but not always, you actually have a convergent series. So this n factorial there goes away if you actually do have a convergent Taylor series. So you can just sum it up. I mean, it's still not trivial in these models to compute these things, and there's beautiful mathematics here. But my point of view is I want to understand this factorial growth and what to do with it. So for that point of view, most of these kind of integral models are maybe not particularly insightful in this question. Another thing you can do is work with Dyson-Schwinger equations. This is a system of equations that recursively encodes relations between different correlation functions. Kind of, if you want to know the 4-point function, well, if you cut up the first vertex, then maybe there's a 6-point function inside, and it's a recursive tower of equations. And you can try to use that. The problem is it's an infinite list of equations, and the equations themselves are complicated integral equations. So again, you can't really do much with it, but you can truncate them. You can say, I only insert certain graphs into each other. And then you get a finite family, which does keep the factorial growth. So you can study some renormalon-like phenomena this way. But the problem from my point of view is that there's a tiny class of diagrams. And then you can always ask the question, well, if I compute something here, I get some contribution to my growth rate. Well, maybe it's canceled by some other diagrams, which I haven't computed. This is a conceptual problem I see with this technique. So what I want to advertise is something else. That's also a simplification. It's not the actual theory. I'm simplifying things extremely. I call it the tropical limit. But it has a connection to the actual integral, which I will try to show you, so that these tropical integrals are actually very closely related to the actual Feynman integrals. So they're a good approximation. So some of them keep information about the relative quantities that they contribute. You can easily compute them, and there's no truncation. All the diagrams contribute. All the subdivergences are there. The series is still factorially divergent. So this is how I got into this. Maybe depending on what your background is, you find other aspects of this whole tropical business more interesting. I'd love to hear. But this was my starting point a couple years ago. So let me just show you what we know. And as I said, we don't really know much. I will go to the basic. Every QFT textbook must have a chapter on phi to the 4th theory, I hope. So I'm looking at a theory where I have a Lagrangian, just a scalar field, quadratic interaction, it may have mass term, and a quartic interaction. And this is just a diagram. So the point is that all these diagrams have 4 valence vertices. That's not really relevant for the techniques I'm going to describe, but to be concrete, think of those kind of things.
Everything will be Euclidean.
I will do everything Euclidean. Yeah. So I'm mathematics and no physics. But even in this Euclidean setting, for example, you can extract phase transition critical exponents from these kind of integrals. But yeah, I'll be Euclidean. Actually, the technique that I do use is kind of tied to the Euclideans. I don't really know how to turn what I do into Minkowski. So anybody, any ideas at the end of the talk, please let me know. So what do we know in this theory? This is it. So after lots of work in the 80s and 90s, and then we know the first 5 terms in this expansion. So what I've written for you is the beta function. For the mathematician, this is like one of the key functions that describes quantum field theory. It's simpler than an amplitude. It doesn't depend on masses and momenta, it's just a function of the coupling. But it's like the first thing, it's supposed to be the simplest thing you can compute. And this is this expansion in this coupling constant, which I previously called alpha, now I call it G. Sorry about that. And a lot of work has been put into computing these Taylor coefficients, which are actually not convergent. And then there was a break of 20 years until we had new techniques and we could compute the 6 and 7 loop terms there. So Oliver Schnetz contributed the 8 loops and 7 loops just a couple years ago. And this is where it stands today. And I don't think we will get much further than that with exact computation. This is already Yeah.
The beta function is scheme dependent, right? So here
Yes.
you present it in MS, but
Yeah.
some of these properties, maybe they could depend on which scheme.
Very good point. So the big question, all of this is, everything depends on the renormalization scheme. So there are divergences which are hidden somewhere. So these quantities only make sense once you define for yourself how do you subtract the divergences, what is the definition of the coupling constant. And of course, if you go to a different scheme, you can make the beta function vanish at the fourth term or the third term. But then you cannot say anything about such a scheme. So this is in the minimal subtraction scheme, which seems to be the most popular. So this is also the one where we actually the most data. So I think this is the only, I think if you go to BPHD or momentum subtraction, I think the beta function is only known up to 4 loops. I don't think people have pursued this further because in practice, techniques tend to work best in the minimal subtraction. So we have of this divergent factorial divergent series, we have the first 7 terms. And we have a conjecture / theorem, depends on if you're more a physicist or a mathematician, what the asymptotic behavior is, right? I told you it should be factorial growth. Then there's maybe some power law, that's so important, and some constant, whatever, right? The key point is this factorial here. And there is a classical physics-inspired method called the instanton method, where you look at the classical field configurations for the action, and that tells you something about it. And so that you should have this behavior follows from that, from pretty straightforward analysis. And it should be pretty much independent of the scheme, but as you know, this doesn't make sense, this statement, because there is a scheme where the beta function truncates. Yeah, but in all the reasonable schemes, you expect a factorial growth here. And then it took a longer time. So in the 80s, there's a paper where this constant was computed for the minimal subtractions. There is some assumptions that go into these path integral, settled point, instanton-like calculations. I mean, for a mathematician, this is all extremely crazy stuff. But these are very good people. They have thought very hard. So let's look how this compares. So what I've plotted here for you is on the x-axis 1 over k. So k is the order in this expansion. So if you go to infinite order, to more and more orders, you should get closer to the origin here. So this is 2 loop, 3 loop, 4 loop, 5 loop, 6 loop calculation.
There is 1 on the axis.
Next slide. So what I've plotted here is the ratio of what we've computed, these things on the top of the slide, ratio compared to this predicted asymptotic behavior. So it should go to 1. And this is where 1 is. It's nowhere. Oh, sorry. Jumped ahead. This is where the 1 is. Sorry, the dramatic effect is it'll go here, you think that it converges, and now do boom. So this series is supposed to converge here. So you can make up your own mind if this says what. So you could say maybe they just miscalculated and it should be a half. Maybe the constant is wrong by a half and it should go here. Looks a bit better. Because if this is really correct, it means even at 7 or 8 loops, we are a million miles away from reaching the asymptotic behavior of this function. I'm trying to convince you that this is the right interpretation. Yeah, so even if you compute something to 8 loops, you're still far off. You haven't touched getting into the area where stuff is behaving generically.
Sorry, does this mean that perturbation here was better than expected or worse than?
Well, it's crazy that you get anything reasonable out that has any resemblance with measurements, right? Why that is, I still don't know. So it is, yeah, the unreasonable effectiveness of something that's a
Divergent series.
Yeah. I just wanted to highlight this fact because often you see calculations at 3 level or 1 loop level or 2 loop level. The last couple of years in the amplitudes community, we have 3 loop, 4 loop has been done for some calculations. We felt when we did this a couple of years ago, we computed the 7 loop thing. We thought we were like so good. We have like 7 loops, nobody needs ever any more. But now I think, well, actually, we're nowhere near enough. Okay. So this is what we know. What do we have to do with this? So just a very brief sketch. There's a big theory of how to properly resum these things with factorial growth, how to get numbers out. I'm just sketching the absolute surface. This is old stuff. This is Borel resummation. Nowadays, a much more sophisticated tools using trend series. The basic idea is you have a series. There was a beta function. You could look at amplitudes. You have some power series and a coupling constant and a variable g. The coefficients grow factorial. What do? You divide the coefficients by k factorial. Now you have a convergent series. So now, at least in a little neighborhood of the origin, you have a well-defined analytic function. And if you know your gamma function integral or the inverse Borel transform, you know that if you integrate that against e to the minus, the integral of u to the k and e to the minus u gives you a k factorial. So this, if you plug the series in there, you reproduce the original thing. So if you can make sense of this integral, you've defined something which has this series expansion up there. And there's good reasons to believe that this particular way of resumming has physical meaning. I mean, you could assign all kinds of values to a divergent series, but there's a good reason to think that this is what you should do. But the problem is, what have I given you? I've given you 7 terms of the Taylor expansion of an analytic function around the origin. And I asked you to integrate it from 0 to infinity. I mean, you can cook up any value, right? I mean, you change the function further down the real line, whatever you want. So there's many problems with this. So first of all, maybe this function, if you analytically continue, it has singularities on the real line, and the integral doesn't make sense. Suppose we're lucky and it doesn't have singularities on the real line, but it could still be that it grows too fast at infinity, so that the integral still diverges. So there's all kinds of problems with this. But we always assume in the best possible world, we assume that everything works as nicely as possible, and that's how you resum these series in practice. And I've spent some time doing this a couple years ago when we completed the 6th loop to get some critical exponents. And it's really embarrassing that you don't get a lot of accuracy out of it. But it's clear that you don't, because you make all kinds of assumptions about a function of which you only know a tiny bit of information around the origin, and you want to integrate. So if you translate what I had on the previous slide to this language, it means that this Borel transform, the series with the inverse factorial and the coefficients, that we kind of know that if you assume this instanton calculation is correct, that this transform function in the complex plane has radius of convergence 1 with a pole at -1. And this is called the instanton for people who know about it.
Wait, the asymptotic you wrote was alternating signs. The computation was not alternating regularly. The 8 loop was, the signs were not plus minus, or what?
They should be.
They are. Okay.
Yeah.
Just to check.
Yeah.
Okay.
Very good. So people in the room who don't know this, this is a good sign.
Yes.
Because if you have a singularity on the negative axis, like at -1, you think of 1 over x plus 1, which is a function which has a singularity at -1. If you Taylor expand it, it would give an alternating sign. So an alternating sign is a signature of a singularity on the negative real axis, which means that you might be lucky to be able to integrate it over the positives. If there wouldn't be an alternating sign, we should be worried. But I try to say we should be worried anyway. Okay, so much for the general philosophy of what to do. And now, how can we probe this? How can we probe this further? So what is the tropical limit? I'm going to present it in an antagonistic way, so this is not how I came up with it, but looking back, maybe that's the best way to explain it. So what I'm doing is I'm taking this phi to the 4 Lagrangian, and I'm smuggling in a parameter. Yes, if you put this psi equal to 1, you have what the box standard phi to the 4 theory I've just written. If you turn on this parameter, you get another kind of theory. If you see for the first time, maybe it looks a bit weird, because if psi is not an integer, right, it's like a fractional exponent of this Klein-Borden operator. But if you're Euclidean, this is an operator with non-negative eigenvalues. You can raise it to any power, it's well defined. Maybe if you see it for the first time working in a real dimension, so I'm also scaling the dimension, which is already regulated to 4 - 2 epsilon. I also scale this by psi. But I got the impression you're already familiar with this, so you can now easily eat the psi factor as well. But now the crazy thing is, now I sent the limit psi to 0. So I'm talking about the 0-dimensional theory with no propagator, kind of. But my claim is that this is a highly interesting limit, which keeps a lot of non-trivial information. And this is the point of this talk, to kind of get you interested in this kind of thing. Here is a picture that tries to illustrate what's going on. So maybe focus on this right part first. So we have a 2-dimensional space of theories on this board. I can think of phi to the 4 theory in n dimension, and I can think of it with different exponents psi. So if you put psi to 1, this would be this horizontal line up here. This is the epsilon expansion, changing the dimension as a regulator of phi to the 4 theory. If you do standard phi to the 4 theory in your 4 dimensions, the Wilson-Fisher fixed point story, you're kind of expanding in epsilon, not here, but around here. Another thing people do is they look at long-range field theory. You fix a dimension, but you look at different quantum field theories where you have different exponents here. if you write it in position space, you can write this interaction as a non-local interaction term, which is why it's called long range, and you can quantify that. That would be an expansion around a vertical line. Fixed dimension, changing the psi. Now, what I'm saying, we should do both and look at the two-dimensional picture. And what you see here, this line, this is the critical line. If D is equal to 4 psi, this is exactly the line when the coupling is dimensionless and it's marginally renormalizable. You have a just renormalizable theory. If you're on the outer side, you're in the Gaussian case, it's not renormalizable. You expect free field behavior. And if you're on the inside, this theory is strongly coupled. Right? So this is exactly this kind of Wilson-Fisher line where you can expand, where the theory is conformal near that line. So this is where the epsilon expansion happens. But if you only expand here in a fixed psi, the normal 4-dimension, you have this fixed point around 4-dimension, that's it. But now we can stay near that line and go to the origin. This is what we're doing. So this means that at every point on this line, on this diagonal here, right, you have an epsilon expansion of that corresponding long-range theory. And it has factorial growth, it has renormalization, it has critical exponents, it has everything. And we just take the limit down there. So in that limit, when psi goes to 0, we still have a variable epsilon left, which kind of, if you think about this picture, it's kind of parameterizing the slope we're coming from. So this is where the tropical theory is at in this point. So it's quite far away if you want to study 4-dimensional phi to the 4 theory. But I think from the point of view of studying asymptotic expansions, and for lots of other reasons, it's very interesting to look at that. Okay, so this is one motivation for what this is. How do we do it? Sorry.
Just a very naive question just before. What are you representing with that green circle here?
This is a zoom. I'm zooming into this corner of the diagram. And this is just zoomed up. So this entire circle here is supposed to be at psi equals 0.
Okay.
But it's suggesting that we still have the parameter epsilon.
So you have direction dependent limit, right?
Exactly.
Yeah, okay.
So and that mathematician would call it blow up. I mean, in this picture, I only have one point down there.
Okay.
So but I'm saying I have a full one parameter family of points down there. That's what I'm sorry.
Sorry, and on the line, do you still need epsilon, still everything divergent, or you can also put epsilon to 0 somewhere else?
I mean, on the line, you have exactly logarithmic divergent integrals,
Okay.
which have holes.
I see.
So you need the epsilon, yeah. So from this point of view, what happens to the Feynman intervals? Does this limit even exist? I mean, it's a crazy limit. You shouldn't expect it to make any sense, right? So sorry, this is a bit technical. So if you can skip this slide, if you haven't seen Feynman integrals before. If you have seen Feynman integrals before, you may know that you can write them in this way. This is the momentum space. We've already talked about the phi to the d half being a convenient normalization. So you have some loop integrals, some loop momenta, and every propagator is a quadratic expression in the loop momenta. And what happens with this psi, right? This is the exponent of the Klein-Borden operator. So in Fourier transform, this gives you the propagator, means just you raise this standard Feynman propagator to a psi. And then the dimension has a psi, and then you take the limit psi to 0. Now this is a weird, I mean, what is that supposed to be, right? So if you go to Schwinger or Feynman parameters, then things look much more tractable. So this is different integral representation. You've already seen the U and F show up in the previous talk as well. So there's certain polynomials called semantic polynomials associated to a graph, and you can write down the Feynman integral in this form. The key point is that the dimension and therefore the psi shows up in the exponent of U. It shows up in the exponent of this ratio U over F, and it shows up in the Gamma function, and it shows up in the exponent of the Schwinger parameters themselves. Yeah, this is just standard textbook stuff. This is nothing fancy, but in this representation, it makes sense to ask the question: does the limit exist? And you can try to compute it. This omega here, this exponent there, as a name, I call it the superficial view of convergence. It's just the mass dimension of the Feynman integral. Naively, think about 4 dimensions. So every propagator is a 1 over p squared. You have every loop, you have 4 integrations. So if you get the number of edges minus loop number times d over 2 is the mass n squared dimension of the integral. But because I'm getting a psi at every edge, at every propagator, and I'm also getting psi from the dimension, this whole psi factors out of the omega. It's really important. So the psi dependence is already in these exponents. And now I want to send the limit psi to 0. This is the formula for these polynomials. That's not really important. They can be computed. What happens in this limit? Very simple. I change variables from the Schwinger parameters x to the psi. These are my new variables. And if you do that, then what happens to these polynomials, right? There are polynomials in X. If you write them in Y, you have to take Y to the 1 over Xi to get back to the X, right? So the polynomial becomes Y to the 1 over Xi. And then you remember there was Xi in the exponent of the polynomial itself. Right? So this is kind of the thing that happens in the integrand. And this limit exists, and it's just the L infinity norm, supremum norm. This is, if you don't remember, you can easily check this. I mean, you have all these sum n, and there's one maximum. In the limit Xi goes to 0. This one term, the 1 over Xi, really dominates all the others. So a polynomial just turns into the maximum of its summand. Yeah, so if you do this with a Feynman integral, you take the semantic polynomial, which is the sum over monomials, which are indexed by spanning trees. And instead of the sum, it now becomes the maximum. So the conclusion is that the limit exists, right? Because you can bound the actual polynomial and its maximum. Right? It's a sum of positive terms, so it's bigger than the maximum summand. And it has a certain number of summands, a number of trees, so it can bound it from above. Yeah, so the actual semantic polynomial, yes?
Sorry, so in the yellow box, I guess you can understand what a max Y means because you're thinking about the power. But in the U polynomial, what do you mean by max X?
So I have, for every spanning tree, I have a monomial, which is in the U polynomial. So if you pick some value of the Schwinger parameters X, but you have to integrate it. So you have to integrate over all values of the X's. If you pick a point in integration space for the Schwinger parameters, you look at all these summands, all these monomials.
Okay, for a given point.
For a given point, you pick the maximum.
Exactly.
So this is a piecewise monomial function. So in a certain region of Schwinger parameter space, a particular monomial will be the biggest one, and then you just integrate that monomial in that region. But of course, you have to switch to another monomial if you swap the regions.
So here was very important that you were Euclidean.
Yeah.
So this is the sum over positive thing.
Yeah. I mean, clearly this bound goes out of the window if you have signs of that.
So in general, you can bring the limit inside the integral, or?
Indeed. So because the integrand has this uniformly convergent limit, you can commute the integration with this limit.
There's certain issues with some higher root non-planar integrals. So there's 5 for that, which
I mean, planar is irrelevant here.
non-planar.
Planar, not planar, is still a sum of monomials.
No, but there can be signs inside these things in general, and the H tables with higher roots.
Sure. I'm talking scalar phi to the 4 now.
Okay.
Now, let's talk about the extensions later. I think these things generalize to QED in some form, but this is still to be worked out. And certainly for this U polynomial, this is for every graph. This is over just a sum of terms. There's no question about the topologization of U. Interesting is the topologization of F, the other polynomial with masses and momenta, and that's a different story. And I have something to say about this, but for the questions later. I should maybe say why this is called the tropical limit. So in algebraic geometry, there's a branch called tropical algebraic geometry, where you also deform an algebraic object, the solution to a polynomial, in a certain way using evaluation, and this is like a baby version of that. And what happens is, right, initially you have this U polynomial, you have a complicated hypersurface that kind of describes for you what's going on. And now you have this big chopped up space in all these different regions, and each region is just a monomial. So somehow the complexity of this hypersurface, which is algebraic geometric complexity, gets now turned into like a combinatorial convex geometric complexity and looking at all these different regions. So these are called tropical hypersurfaces. And this is why I've given it that name, although I'm not actually using lots of tropical algebraic geometry. I'm just staying on this combinatorial convex geometric quality. Okay, so what happens? Sorry, what happens to the integral? I have a bit of a delay here. What happens to the integral? So the actual Feynman integral now gets a superscript trop for tropical. And what happens is in the integral, you get this, everything becomes tropical, the polynomials become tropicalized. And one thing I have glossed over is what happens here, that the coefficients go away. Yeah, in this tropical limit, you don't see the coefficients. Because any constant number to the 1 over xi, it's kind of beaten up. So actually this tropical limit, in this case where I make every edge massive, doesn't depend on kinematics. Yeah. So this is very weird if you think about it from a physics point of view, but there is a way to take a tropical limit which retains the dependence on kinematics, but not in this term. Okay, so I'm taking this. So no amplitudes for now.
Did you say why F disappeared?
I have not really explained that. It's kind of you do the calculation, you show something, and in this particular case, because I have a mass everywhere, there's a part in F which is just U times the sum of the masses. And all the momenta, they come with some monomial. They also appear as a monomial from the mass terms. So if you only look at which monomials are there, you can forget about the momenta. If you put masses everywhere, all the monomials show already up only in the mass term. And then the mass term itself, the F is just U times the sum of all the variables. So you just get a different power of the U and the sum of all the variables. The sum of all the variables gives you this thing, and this is why what's left over is just a U thing. So the way we set it up for this first paper is that we're calculating in a totally massive scheme. You put masses everywhere, and that allows us to put all the momenta to 0 and compute beta functions that way. It's called the massive tadpole scheme or something. It's very convenient for this tropical context. What I wanted to highlight here is that all of these integrals, they have a pole when omega is 0, yeah? And they become logarithmically divergent. And this H, this is historically the thing that I studied first, I call it the Hep bound, is the residue of this thing. Now, there is an analog for the actual Feynman integral, right? If you take the actual Feynman integral, it also has, it's a meromorphic function, it has poles in epsilon in the dimension. If you look at the residue, when in the dimension where the integral becomes logarithmic, the residue itself is a number, we call it the period. It has been studied by Bloch and Deneau and Francis Brown and de Kruijmer for many years. There's beautiful algebraic geometry here, which is determined by this first semantic polynomial. So I just want to mention this because maybe you have heard about those things over the last years or so. And there's a tropical analog of this. So conclusion is this limit exists. You can write down a formula, and maybe tropical isn't such a bad word. These are some examples of the actual Feynman integrals. Yeah? So I'm working in 4 minus 2 epsilon dimensions, standard phi to the 4 theory. I look at logarithmic divergent graphs where the omega is 0. So those are the ones that contribute to the beta function, to the renormalization of the coupling. If you compute a Feynman integral, right, it depends on the masses, momenta, whatever. In this case, if you don't have subdivergences, it only has a simple pole in epsilon. In general, it will have higher order poles, but for these graphs with subdivergences, it only has a simple pole. And because it's logarithmically divergent, it doesn't have any mass dimension. The residue of this pole is independent of kinematics. And this is this P, what we call the period. Yeah. And here's just some examples. If you take this bubble graph, it turns out to be a 1 over epsilon plus stuff. If you look at this graph, there's a 6 zeta of 3 over 3 epsilon plus stuff. So you get all kinds of interesting numbers, zeta values, if you just look at the 1 over epsilon poles of these diagrams in the actual theory. Yeah. And as I said, there is a lot of information about this. So they are interesting because they contribute to the beta function, the most difficult part from a number theory point of view that goes to the beta function. And we have lots of data, polylogarithms, modular things, Calabi-Yau surfaces. All of this complexity shows up even in these beta function coefficients without any kinematics. What happens now in the tropical theory? These things get much simpler. So this is an example of the tropical pole in epsilon of this bubble graph. So this graph has only 2 spanning trees, one edge or the other. So this U polynomial is just x1 plus x2. Now we replace this by max of x1 and x2. I'm supposed to integrate 1 over that squared, and there's a homogeneity projectivity thing going on. So you can set one of the variables to 1 and just integrate the other. So this is the integral you have to do. And I did it for you. You have to split up. When is one monomial the maximum? When is the other the maximum? You integrate, you get 2. Yeah, for comparison, the actual integral was 1 in the 4-dimensional theory. In the tropical theory, the same graph evaluates to 2. So it gets bigger. It's an upper bound because the u is in the denominator. We make the u smaller because we replace it by 1 monomial. So the integral gets bigger. Now, this is a horrible way to compute things, right? If I have to look at all these monomials and look at each, I mean, this example it goes, but if you have a big graph, you may wonder, is it even possible to compute that tropical thing? This is a whole other story. I'll just mention you can compute them. So they're easy to compute if you know how. This bound for the polynomial u descends to a bound for the actual Feynman integral. So the tropical one is an upper bound of this residue of the actual one, and there's a lower bound given by 1 over the number of summons. They have some beautiful identities which exactly capture identities of the Feynman integrals. Talked about this at other occasions, not today. So the really cool thing I want to stress today is this correlation. So this is a table with meaningless labels of the graphs of some table that Oliver Schnetz once wrote up. So this is just a list of 7 loop graphs in a certain table. And here you have the residue of 1 over epsilon of the actual Feynman integral. It happens, this is the order where we know them. To 7 loops, we have computed all of them. So these are approximations, but we have exact polylogarithmic expressions for all of these. This is the tropical one. They turn out to be integers for these graphs. And there they are. And I ordered them by magnitude. So you see somehow the bigger ones are bigger, but there's a big overall difference. The tropical ones are much bigger, but they seem to capture the relative order of things. And then you have to plot them, if you can imagine this in your head. So at some point I plotted this data and I was very surprised to see this thing. So this is the same data from the table, but as a plot. So on the x-axis, you have the tropical Feynman integral. On the vertical axis, you have the actual Feynman integral. So there's 2 orders of magnitude difference in these scales. But you see an amazing correlation. Yeah. So if you now give me a new graph that I haven't computed, I can easily compute the tropical one, and I kind of can guess up to 1% what its period will be. Yeah. So the point of this slide is just to illustrate that even though these tropicals are very, very different, I turn a polynomial into a maximum, looks nothing like a Feynman integral. They somehow capture a lot of information about the relative size of contributions from Feynman diagrams. And they even allow you to approximate the actual Feynman diagram up to 1%. Michael Borinsky has, over the last years, turned this into a much more fancy machinery, where you use this like as the first approximation, but then you can do a Monte Carlo integration around it and get even higher accuracy for Feynman integrals from this tropical approach. Yeah, so one way to think about tropical Feynman integrals is also just as a means to approximate Feynman diagrams. This is how I initially got into it. But I think maybe for physics connection, it's more interesting to think of them as this limit of long-range theory. So this is what the tropical theory does for you, but this was for diagrams without subdivergences, right? There was only simple pole and epsilon. I didn't need to talk about renormalization schemes or anything because these things are scheme independent because they only have a simple pole. And the main point of the paper that I'm talking about today is that we kind of make the claim that instead of just using it as a trick to approximate primitive diagrams, you can also do everything with subdivergences and do standard renormalization, and you actually get a more fully fledged quantum field theory interpretation. So what we've done now is we do minimal subtraction. So I do everything in epsilon. I compute all of these tropical integrals in epsilon expansions, also for graphs with subdivergences. For any graph, I can compute this. And it turns out that this tropical integral is always a rational function of epsilon. If you know Feynman integrals, this is the key simplification. Feynman integrals are usually gamma functions, hypergeometric functions, all kinds of crazy things. And in their epsilon expansions, you get these Calabi-Yau periods and all these crazy things. In the tropical limit, everything is a rational function with rational coefficients. This is the huge simplification. Now, if you have this rational function with an epsilon, you can do standard minimal subtraction. You do the BPHZ formula, you subtract the counter terms, and then you extract the pole. So you can define the renormalized quantities and the beta function just like in the standard textbook approach, just that you swap the Feynman integral for this tropical one, which are these rational functions.
So are you still considering this limit where you can, the kinematics don't,
I'm still doing this. You can do the whole thing with a limit that has interesting kinematics. But if you do that, then still the beta function will be the same as the beta function in this fully massive setup. Kind of what I'm doing in this bigger picture where I do have the kinematics, what I'm doing is I'm computing all Feynman diagrams at 0 external momenta with the same mass internally everywhere. And that's enough information to get the beta function. And of course, it makes things much simpler because now I just have a rational function on epsilon instead of whatever the complexity of a tropical kinematic dependence is.
Okay, so you don't know. That was my next question.
I don't do that in this talk, but I have some examples of tropical Feynman integrals with kinematics if you want to know.
Yeah, sure.
They can be defined, they can be computed. You can learn something about lambda singularities from the tropical limit. Very fun, but yeah, another paper.
And
Yes.
in this case, I mean, if you take a higher order in this psi, a limit that you're taking, does this rationality continue? Or?
No, and I think it's a very interesting question to see what happens at higher orders in psi. I don't think anything has been done. Super interesting, yeah. If you want to look at this, I would highly encourage it. I mean, at some point, you must see the periods appearing. But you could hope that maybe to the first or second order in psi, things are still, they won't be rational forever. But Short answer, yeah. Beautiful question. So what we can do now in this tropical setting, we can, for every graph now with subdivergences that is higher orders than epsilon, but if you do this BPHZ procedure, you can extract its contribution to the beta function. So still for every graph, you can associate a number, which is its contribution to the beta function in that renormalization scheme. And now we can again do a plot like this, and this is what you get. So this is now for 6 loops, not for 7 loops. On the x-axis, again, you have the contribution to the tropical beta function of the graph. On the y-axis, you have the contribution to the actual 4-dimensional beta function in the minimal subtraction scheme of these graphs. The red dots are the ones without subdivergences. So that would be the analog of the plot previously. There's only 4 points here because it's 6 loops, fewer graphs. There's only 4 graphs. And 6 loops in that without subdivergences. And the blue ones are ones with 1 subdivergence, and the orange ones are ones with 2 subdivergences. And it's really quite amazing. So you see 2 things. The ones with subdivergences are smaller, which is not surprising because it's subtracting stuff. Yeah. What is surprising that this correlation also persists. So even because you're subtracting things, this tropical approximation still captures this high correlation. So
the slope is not the same.
Sorry?
The slope is not the same.
I mean, you can waste so much time trying to fit different curves here and trying to guess how it depends on the loop order. And I suggest try not to do it.
The correlation widens as well, right? Yeah, in black.
Of course, there's a big mess very down low. So the black ones are the ones with, I don't know, 4 or 5 subdivergences. But then kind of the idea is this becomes statistic. First of all, they're very small anyway. Some of them are positive, some of them are negative. So it turns out that they actually don't contribute much to the asymptotics of the function anyway. So you shouldn't be too worried about the fact that down there, it's just a big mess because you can forget about it anyway. There was even a conjecture for some time that the asymptotic behavior of the beta function is dominated only by the primitive ones, by the red dots. And this is only with this new data that we can finally refute that. So it seems that they give like 50%. But still, this is a tiny number of graphs, and this is a huge number of graphs, and they really don't contribute much. Okay, so we have established that this tropical, the correlation between tropical and actual Feynman integrals is not just true for the graphs without subdivergences, but even with subdivergences when we do standard renormalization in the minimal subtraction scheme. We cannot really check this in other schemes because we don't have 6-loop data in other schemes that we can compare to 4 dimensions. But in our paper, we compute the beta function also in a BPHD kind of scheme, in the tropical case, but we can compare with them. Okay. Maybe we should cut it a bit short on this one. I just wanted to illustrate that how do you compute these things? Right now, I give you a big graph. It has 1 million spanning trees, so you have to take a maximum of 1 million monomials and then integrate this. Seems a bit daunting. But I wrote a paper a couple of years ago where I studied this from a combinatorial point of view because you can translate this into a purely combinatorial question about the sum of all permutations of the edges in a graph, and then for each permutation there's associated some quantity, and you can simplify things. And in the end, you can write down this tropical Feynman integral for a graph in a formula like this, where you're summing over all flags, maximally nested chains of 1 pi subgraphs, and each of them gives a contribution. So this is just an example for this 3-loop graph, which in 4 dimensions gives you a 6 zeta of 3. In the tropical world gives you an 84. If you know that zeta of 3 is roughly 1 point something, it's much bigger than 6 times zeta 3. But how do you get this 84? Well, if you look at this graph, you want to take a chain of a 1-loop graph inside a 2-loop graph inside that graph. So you can either start with a triangle or with a square. And the next step, you have to make this 2-loop graph, which is only 1 edge missing. These are the only ways you can take a 1-loop graph inside a 2-loop graph inside that graph. Only these 2 possibilities. And then what you write in the numerator is the number of edges. So here you have 3 edges. You add 2, and the last one is the 1. This is the 3 times 2 times 1. Here you start with 4 edges. You add only 1. Then there's 1 missing. This is the 4 times 1 times 1. And in the denominator, you write the power counting, the mass dimensions. So this is 3 edges minus 1 loop times 2, because 2 is half the dimension. So this is 3 minus 2. So this triangle would be a quadratically convergent diagram in 4 dimensions. So this is this 1. And this has 5 edges, but 2 loops. This also gives you a 1. And here the 2 comes because the box in 2 dimensions would be quadratically convergent. And then you get a factor just of how many different ways there are, right? How many different triangles you can choose, how many squares. And this is how you get this 84. So the point of this is, well, that's how you can compute them actually on a computer quite easily for big graphs. But it really actually shows you a recursive structure. Because it shows you that, well, at some point at the last step, right, you have to delete it one edge and go one loop down. And now there comes the key observation here that even with this tropical theory, I could maybe go to 7 or 8 loops, but I mean, at that point, you're already talking about a lot of diagrams. Now, the individual diagrams are kind of trivial, but you still have an factorial growing number of diagrams. So what you really want to do is you want to work with the entire sum of all the diagrams and not split them up into individual ones. And now you sum over all graphs, and then for each graph, you have to sum over all ways of nesting these graphs inside. Then you can start to see a recursive pattern in terms of just the sum of all things. So if you think about, for example, a two-loop thing, the sum of all two-loop graphs, then in the last step of this flag, you must have had a one-loop graph and then added one more loop. So this extra loop you added in the last step, right? It has a certain number of edges. And then there was a one-loop thing here. And then you're summing over the different ways how you can distribute the edges between the sub and the rest. So this is just a schematic picture. It looks a little bit like a Dyson-Schwinger equation. If you add it all up, this gamma is the sum of all the graphs of a given loop order, the effective action, physicists would say. And if you package it all up, you can either write it as recursion relations between these gammas, or if you put them all in a generating function, you can write it as this nonlinear PDE in two variables, where the variable t is counting the coupling, and the variable x, you need an extra variable to count the number of legs. Because if you're opening up the loop, you're creating two extra legs. So this recursion is in the loop number and the leg number. This is always the thing with Dyson-Schwinger kind of things.
Isn't this Wilson-Konchitsky equation? So when people write it RG formally by doing like scale by scale, I mean, you can either like split things into two or close a loop.
Yeah, so there's similar looking equations. Forgot the name. In terms of the Wetterich equation, I think is also related to this. So yeah, I don't quite exactly understand the relation here. One of the problems is that we get this recursive relation, but our recursions are for Green's functions with a zero external momenta. And in the normal Dyson-Schwinger equation, you would say you have to integrate the subgraph over the extra loop momentum or something like that. Or you put different scales on different loop momenta.
Wilson-Konchitsky is for the effective action, so like vacuum drive.
Well, effective action still has kinematic dependence usually. But
yeah,
I mean, let's chat about it. But there's definitely equations similar of a similar flavor. I showed up in other places, and it is morally just writing down a kind of Dyson-Schwinger system of Dyson-Schwinger equations for a generating function. The key point is that normally for Dyson-Schwinger equations you have integral operators. You have to integrate over the subgraphs. In this case, you just multiply with 1 over omega. And this allows you to turn this in an ordinary, there's no fancy operation here. This is just a standard PDE. So I hope as unfortunately I'm not good with nonlinear PDEs, maybe in a couple of years you will tell me this is just some penalty, I don't know, whatever kind of crazy function. At the moment, I don't know. But the key point is that this allows you to go to very high loop orders. So if you want to know the 400 loop 4-point function value, you also have to start with the 400 leg 1-point function, and you fill out that triangular kind of matrix of Green's functions, and that's what we've done. And we've generalized it also to ON symmetry. So if you have n scalars in a symmetric setup, you can incorporate that easily. So I should say this idea of using this recurrence relation to describe these tropical time intervals has been, Michael Borinsky has been thinking about this for many, many years, even before the actual papers came out, the last couple of years of the tropical Monte Carlo. So this idea goes way back, but putting it together with a renormalization, because for that you need the epsilon to make sense of subdivergences. This is somehow what we're doing. So you can now throw renormalization on this and write a similar equation for the renormalized Green's function, and then you can take the limit epsilon going to 0, and things become tractable. So I should maybe wrap up in five minutes or so. So let me just show what we can do with this. What do we learn from all of this nonsense? So let's look at tropical 5 to the 4. So this is the tropical minimally subtracted beta function. The first couple terms, I mean, I could have compared it to the other, but you know, there's a couple of orders of magnitude between the coefficients. But they have alternating signs, and we have now 400 of them. So with 400 terms, you can start making some serious analysis. You can actually start looking and get confident ideas of what's happening. And you can easily check these definitely grow factorial. There's like a little power law. there is a factor of 3 to the n at every order. This is the kind of thing you expect from an instanton with a certain action. And actually, we've done that calculation. So it's a bit weird, but you can do, you can just take the instanton calculation approach and apply it in this long range dimension regularized setting, because the instanton that people use is like a radial symmetric function. So you can, without any problems, extend it to a dim reg. And if you do that, you indeed find that in the tropical limit, the instanton is at -1/3. So what I'm saying is that this, what's in front here is really compatible with the standard instanton expectation stuff. So that's a plus for the instanton. So maybe that's actually correct.
And before there was a 7/2 instead of a 5/2.
This is also explained because part of the exponent is the dimension.
Okay.
And because you go from 4 to 0, and there's a 1/2. So indeed, also the exponent, very good point. So indeed, this stuff, what's surprising is the correction terms. Because normally, if you look at these instanton papers, the expectation is you get corrections in 1/n. So there should be a 1/n, 1/n squared, 1/n cubed. And there's even papers who have computed what the 1/n correction for this expansion is in minimal subtraction, for example, for the beta function in 4 dimensions. I mean, it's a very complicated thing. There's lots of mathematical assumptions. They don't all agree with each other. But in principle, the instanton setup should allow you to compute higher order corrections here. What we found surprisingly is that we have fractional powers. So this is without doubt. I mean, with 400 loops, you can definitely say that you can rule out a 1/n correction. There's a bigger correction, which is only 1/n to the third. And then there's a 2/3. And if we can go further down, because we have 400 terms, we even see a very clear sign of a logarithm suppressed with 1/n. So the conclusion here is that this instanton, this first instanton singularity, is much more complicated than at least I expected. So if you translate this asymptotic behavior to what it means for the Borel transform, then it turns out that this is not just a simple pole or branch cut that starts at -1/3, but it's a confluent singularity where you have like the expansion, the third roots, and you have logarithmic singularities. We actually, with 400 loops, we already see a second logarithm. So it's going to be a log n squared over n squared. And I don't think the data is confident enough to exclude that there might even be further logarithms. So my takeaway from this is that the instanton is much more complicated than one might have expected. And for me, I would really love if some people who know the instanton kind of calculus could tell me, calculate the tropical limit and explain where this comes from. Because it could hint at something that you missed about the instanton, which is maybe also present in 4 dimensions. I mean, somewhere between 4 and 0 dimensions, these fractional power corrections have to be switched on. So maybe they're even there in 4 dimensions, I don't know. So this is one main takeaway. The other takeaway is something I already alluded to. What is this diagram doing? If you have a series that grows like n factorial with the power law, the first thing you do when you try to analyze a series is you look at the ratios of consecutive terms. That's good because the overall constant drops out, and this a to the n just becomes a factor. And the only thing that you then see, you multiply by another n to get the factorial go away. And then this ratio should go to 1/a, so you should read off the position of the instanton. And from the 1/n correction from the slope, you should read off the power, this 5/2. Even if you have the 1/n to the third kind of corrections, if you look at this ratio, it's still of this form. Yeah. So now I really should have prepared the slide better and have another showdown moment. But if you only look at the left part again, so like up to here, this is like 25 loops. Or maybe let's say we go to 18 loops. Yes, suppose we've computed longer, we computed 18 loops of the tropical beta function. If you plot this ratio, you see a beautiful line. And you would think, hurrah, we're in the asymptotic regime, it behaves exactly like 1/n. And you would read off that the instanton is at -1/2.65, and the exponent in n is 6.4 and not 5/2. But then actually, if you go to 50 loops, you say actually this curve starts sloping, and this is the real behavior. So this is just another way to hammer home the fact that even if this is really deceptive, this looks so linear. And if you and this part of the plot we can do in 4-dimensional theory because we have the 7-loop data. So if I look at this ratio stuff, also in the 4-dimensional theory, it has exactly this behavior. And that's why for a long time we thought maybe this calculation with this coefficient from the very beginning was wrong because it seems to go somewhere wrong. But now in the tropical theory, we clearly see it's just a low order effect, and you have to go to much higher loop orders to hone in on the asymptotic behavior. And final comment. Now with 400 loops, you can look at the analytic structure in the Borel plane. So you divide by n factorial. Now you have an analytic function. You have 400 terms of the Taylor expansion of this analytic function. And now you can try to assess what does it actually do. This is the very basic thing. You approximate it with a rational function. It's called a Padé-Borel approximation. And then by looking at the poles of this rational function, which approximates this, you get some idea of where the singularities of the function are. There's always some, if you do this, there's always some spurious poles which are not stable. So forget about these 2 points. They disappear if you look at the next approximate. But you see features. There's definitely a clustering of singularities at -1/3. There's another cluster at -2/3, and here -3/3. This is in line with what people expect from instantons. Yeah, so from instantons, we know the first singularity should be at -1/3. And you would expect it to be branch cut. I mean, we've seen it's not just a branch cut, it has these logarithms and so on, but let's take it like this. But then you expect that if you have one instanton, there should be 2 instanton solutions. 2 instantons far away should roughly solve the classical equations of motion. So you do expect this infinite sequence of singularities on the left-hand axis. And indeed, that's what we find. So at least that's good. The other thing we find, there's nothing on the right. And nowhere else. Yeah, these tails are just the way we've transformed these things. So they all converge in the end to these branch cuts. So it looks like the minimally subtracted tropical beta function is really Borel summable. You have no obstructions to summation on the positive real axis, which some people expected, but there's a huge debate whether renormalons are there or not. And it's dependent on the renormalization scheme. So if we go to a kinematic renormalization scheme, so we did a BPHZ calculation, all kinds of crazy things happen. So the instanton picture roughly looks the same. This is the plot with lower loop order, so that's why it doesn't resolve the higher ones. You see branch cuts on the positive axis. This is also in line with expectations if there is a renormalon. So the renormalon is there in this scheme. It's not there in the minimal subtraction scheme, in the beta function. Another surprise we found is that the instanton, even though it's at the same positions, it has a different structure. The exponent of the instanton is only 3/2, not 5/2. So actually, the beta function of the BPHZ scheme is only 1/n times the beta function of the minimal subtraction scheme. And this I'm really puzzled by, because this exponent is usually explained by simple dimension analysis in the instanton approach, and all the work in the instanton approach is in computing this constant. So I would love an explanation of this 3/2 from somebody who knows instantons in BPHZ schemes. And we really can measure these renormalons extremely accurately. But unfortunately, you cannot compare to anything because the renormalant amplitude is famously uncomputable. Okay, so let me just summarize. From my point of view, we still know very little about the asymptotics of Q of t. I hope I convinced you that from this point of view, if you look at the asymptotic growth of these coefficients, the convergence to the asymptotic is very slow. Maybe around 20 loops, you're kind of starting to see what's happening. I haven't really talked about how the resummation works, right? So now you have to somehow take this function and literally continue to the positive line, integrate it with this exponential. So there is a lot of ingenuity that goes into how people do this. But I think what one should try to do is to take this data that we have and really try to study that context. Why does it work so well the way people do it? Maybe we can do even better if you look at how the functions actually behave at 400 loops and try to incorporate that. The tropical limit is an interesting new toy model. I've focused on the practical that you can compute it and that it has this correlation with the real theory. I also personally find it very interesting because it's just a combinatorially interesting thing to play with as a combinatorialist. Also tells you about identities between Feynman integrals, which I've been studying for a long time. And then finally, my main surprise was that the asymptotics seems to be much more complicated than just a simple expansion of 1/n. So let me leave it here, and thanks for your attention.
Thank you very much, Erik. Any questions?
So there's another large little n limit that is famously asymptotic in quantum field theory, which is in the number of legs, not in the number of loops. And there I think we only have one example in phi to the fourth. So if you take an amplitude near threshold, there's these old papers by Danson and friends where they use the classical equation of motion to actually resum the amplitude, but near threshold in the massive case. But I think it's the only data we have about large number of legs.
Yeah.
Where also the diagrams explode. I mean, you don't have the integrals, which are at least at tree level, you wouldn't have the integrals. Does this?
We have not looked at the large leg behavior. Thanks for suggesting that. Yeah, sounds fascinating. I will look into this. I mean, all these limits, large legs, large n, or special values of n, because you have, like, I'm talking now about capital N, the ON vector model n, but there's a unit integer on the large n limit of the 5-4 model. So I would suggest people to do the same thing in the tropical, right? We have a differential equation for the solution. Then the large n somehow must become integrable, because in the 1/n expansion we can exactly solve things. So I think this is a great laboratory to really see this transition from the generic behavior to the large n behavior, which is very different. A large n power series is convergent, finite n it's asymptotic, and somehow how can we use this large n information? That's something I've also been struggling with. There's a lot of large n data, but I don't know how to incorporate it when I want to resum finite n calculation. So yeah, but we have too many things to be done. But I think it's super interesting. Thanks for the lecture, Jess.
If you do Pade directly on beta of G, in the G expansion, do you see the structures or they are lost? You need to bother.
I mean, if you do Pade on beta directly, to be honest, I haven't done it. But because you have factorial growth, if you fit a rational function to factorial growth, you have an essential singularity.
That's seeing poles, so you should see.
No, I mean, then you have this essential singularity at the origin. So, to be honest, I don't even know how it looks like, but
Okay.
I don't think it will allow it to resum. But what we have seen is that, yeah, so we've looked at one thing. So if you do Borel transform,
yes.
Now in the Borel plane, you do the Pade-Borel.
Yes.
I've shown you certain properties about the poles. There's another thing that happens, which wasn't visible in this plot. You can also look at the zeros of the Pade, not just the poles. And the zeros also form a certain pattern, and this is indicative of an essential singularity at infinity on the right. So what we see is that the Borel transform beta function has an exponential growth at infinity. This is something we can also see by looking at the zeros of the Pade. So you should see something that's, well, I don't know, without the Borel transform. But this is important because it means that if you want to resum it back to the actual beta function, it should have a singularity at some point. At some coupling, there should be a singularity on the other axis, which is confusing because people often, when they do this resummation, they assume that the Borel transform grows like a power law and fit functions like that. But we see clear signs that it's exponential, and that's what you should do. Yeah, thanks.
These zeros, are these interpretable as some like complex CFTs or something like that?
The zeros of the Pade approximation of the Borel transform beta function. I don't know. They seem to form into a stable pattern, though there seems to be some structure behind that. I don't know what it is. If you have an idea of that.
Yeah, it's a question instead of Pade, because you expect it's converted on the polar negative axis, yeah. You should make a cut and change uniformization of C minus cut.
Yeah, the conformal method. Yeah.
Conformal method, yeah, and see much better precision how it goes in positive direction.
Yeah. So this is for the resummation. You do this change of variables where the cut goes on the unit circle, and that's how we actually determine the. So what I've shown you here. I mean, how do we get this? How do we get this kind of information here? We have determined these C1s and C2 and C3 to like 10 digits from our data in the tropical. How do you do this? But it's very bad to do these kind of ratio things on the series. Convert us very slowly, and or maybe we're not being very clever. But what we do instead is we work in the complex plane. We Borel transform. We change the variables to a conformal plane, or to further simplify the singularity. But you can change this. You can furthermore go to the third root coordinate, where this singularity becomes really just a branch path after the long run. And then we use differential approximants, so you can try to guess a differential equation that function would fulfill, and then analyze the regular singularity of the differential equation. So it's an old method called the differential approximant method that we found that we use to actually assess what this behavior is. But for once we finally, hopefully at some point in my life, we get to resumming these things, definitely conformal plane is the right thing to do. But what functions to try to use to fit as a basis? That should be something with an exponential singularity at 1 in the conformal. Okay.
Then let's thank Erik again. And we will resume on March 4th.